Hello everybody and welcome to section 4.4 where we're going to talk about indeterminate forms and L'Hopital's rule, which is a very useful rule for evaluating limits. So we're going to kind of take a break from the graphing, talk about some of this stuff, and then in the next section after this we'll get back into a lot more graphing where we'll actually look at some limits, as x goes to infinity or negative infinity. And look at things like vertical asymptotes in the next section. So we want to get a good understanding of how to calculate some more complicated limits, but we don't want the work to be more complicated. So there were some situations, back in the early chapter 2 stuff where we were given some limits and we had to play a bunch of algebraic tricks in order to figure out what those limits were, because if we tried to just evaluate them directly, and what I mean by that is simply, if x goes to a, just plugging in a and seeing what we get, we may have come across some indeterminate forms already. And those are things like 0 over 0. You can't divide by 0, you never get information out of this thing. Or infinity divided by infinity. Right? That's not infinity, that's not 1, that's not 0. So we had no idea what these things meant. They were all undefined for us. If we had something like 0 times infinity, again, infinity doesn't play the same games like normal, straightforward real numbers do. Infinity is a concept, not a number. So that's called an indeterminate form. We also saw maybe some things where we saw infinity minus infinity. That's not 0. Some things grow a lot faster than other things. Some infinities are not made the same as other infinities. So that is not going to give us 0 just because we see the same thing being subtracted. Again, subtraction and multiplication, those are things that real numbers use for operations. These are not real numbers, right? These are just concepts. So those operations don't behave the same. 0 to the 0, we always say this kind of loosely. We say anything to the 0 power is 1. Well, when you get 0 to the 0, that's kind of an undefined, risky business there. Or infinity to the 0. If you have something infinite and you raise it to the 0 power, what is that? And then 1 to the infinity. Right, 1 to any power is 1, but what if that power grows as large as it wants, as fast as it wants? Is anything funkier happening there that we need to investigate? So these are all what we would call indeterminate forms. If we try to calculate a limit right away and we see that one of these pops up, then we know we're in trouble and we've got to try something different. And in some situations, we couldn't play with it algebraically to get it to work out nicely. So that's where we're going to need this more important rule, which is L'Hopital's rule. So L'Hopital's rule goes a little something like this. It says, suppose f and g are differentiable. We're going to be dealing with two functions, f and g. And g prime is not equal to 0. You'll see why in a second. If, and I'm going to separate it up into like two cases. Case 1, the limit as x goes to a of f of x is 0, and the limit as x goes to a of g of x is 0. Or case 2, the limit as x goes to a of f of x is positive or negative infinity, and the limit as x goes to a of g of x is positive or negative infinity. Right. So we want either both limits to be 0, or we want both limits to be infinity. We don't care about the sign on infinity as long as it is infinite. Then as x goes to a of f of x divided by g of x is the same thing as the limit as x goes to a of f prime of x over g prime of x. So what this allows us to do is to differentiate the numerator, differentiate the denominator, and look at that ratio instead of f over g. We look at f prime over g prime. Now, quick note, this is not the quotient rule. Right? There is a quotient here, but you don't differentiate this whole function using quotient rule. Right? This is not derivative of the top times the bottom minus the top times the derivative of the bottom all of the bottom squared. That's not how it works. We just differentiate the top, and then we just differentiate the bottom completely separately. And we look at the ratio of the derivatives rather than the ratio of the functions. So this is what is known as L'Hopital's rule. So if you're trying to evaluate a limit and you get something like 0 over 0 or infinity over infinity, then you get to use L'Hopital's rule. Notice this is an if-then statement. If the limit as x goes to a of f of x is 0 and the limit as x goes to a of g of x is 0, then you get to use L'Hopital's rule. Or if the top is infinite plus or minus, the bottom is an infinite limit plus or minus, then you get to apply L'Hopital's rule. Some people just look at two functions and they say, oh, cool, I use L'Hopital's rule. Whoa. Well, did you verify that it works? Because if the limit of the top is some sort of, positive number like 7, right? And then the limit as x goes to a of g of x on the bottom is, some sort of number like 5, well, then your limit is 7/5. You don't use L'Hopital's rule. You might run the risk of getting something different when you use L'Hopital's rule. Or you might start differentiating things down to 0. Right? So you do want to be careful. Make sure it actually fits the criteria for L'Hopital's rule. Either both top and bottom limits are 0, or both top and bottom limits are infinity, plus or minus. Then you get to take the derivative of the top and the derivative of the bottom. And this limit is usually, in general, easier to evaluate. You may need to use L'Hopital's rule again, right? Because maybe this limit is still 0 over 0. Then do the second derivative of f over the second derivative of g and look at that limit as x goes to a. If you still get 0 over 0, you can use L'Hopital's rule again. Right? So it's nice that it just keeps on going. So let's take a look at an example of a limit. Let's say we want to find the limit as x goes to a, as x goes to 1, right? We need some sort of value here. Natural log of x divided by x minus 1. So here is a case where no amount of algebra is going to help you out, right? You can't just multiply top and bottom by the conjugate because it's not going to clean things up for you, right? There's nothing we can do to simplify its log, right? In the numerator, we can't factor or clean anything up. So we're kind of stuck. And if we look at it at first, when we try and plug in 1, we would be getting natural log of 1 over 1 minus 1. Well, natural log of 1 is 0. 1 minus 1 is 0. So this is one of these indeterminate forms. But now, that's actually good to see because that means immediately we use L'Hopital's rule, right? This gives no information, right? This is basically useless. Right? This does not say the limit's 0. This does not say the limit's 1. This does not say the limits does not exist or infinity. This is useless information other than the fact that it immediately tells you, go use L'Hopital's rule. So that's what we're going to do. The limit as x goes to 1 of natural log of x over x minus 1 must be equal to the limit as x goes to 1. Again, I simply differentiate the numerator. The derivative of natural log of x is 1 over x. I simply differentiate the denominator. This is just a linear function. That minus 1 is gone. I just get 1. So I'm evaluating the limit as x goes to 1 of 1 over x, which is simply 1 over 1, which is 1. Right, so again, this does not tell me, oh, same thing over same thing, that's got to be 1. That is bad logic. This does not tell you that the limit is the number 1. You're just getting very lucky if you make that guess. Again, that's a guess. Like using L'Hopital's rule, I differentiated the top, I differentiated the bottom, and I looked at this limit instead, right? 1 over x divided by 1 is still just 1 over x. So that became a very easy limit to evaluate. All right, so now that we have more functions at our disposal, this L'Hopital's rule will be very useful. We even have seen more stuff with the exponential function as well. And even if we look at limits that go out to infinity, e to the x over x squared. So even though we have this limit that goes all the way out to infinity, the rule still applies. It doesn't matter where x goes to, but what matters is we hit one of these indeterminate forms, which we do because if x gets arbitrarily large, the numerator gets arbitrarily large, right? E to the x just blows up. So does x squared, right? Y equals x squared just blows up. The larger x gets, the larger y gets. I should say the larger x gets, the larger x squared gets. The question is, does one grow faster than the other, right? Is the numerator blowing up way faster than the denominator, meaning this number is getting really huge? Does the denominator grow faster, meaning it's actually turning into a fraction with a large denominator going to 0? Does it level out somewhere in between at the number, who knows, right? 40 pi? Like, what is this limit? This gives us no information because it's an indeterminate form. So we use L'Hopital's rule. The limit as x goes to infinity of e to the x over x squared. Apply L'Hopital's rule and we get, well, the derivative of the top, e to the x, is e to the x. The derivative of the bottom is 2x. You look at this again and you say, well, wait a minute, the top's still going to be infinitely large. 2 times infinity is still infinitely large. So what can I do with this? Well, it's infinity over infinity. Apply L'Hopital's rule again. It still applies. If I looked at these as my original functions, I would just take the derivative of these functions, numerator and denominator, and use L'Hopital's rule, so let's do it. Differentiate the top. Oh, it's still e to the x. Differentiate the bottom. Oh, I just get 2. Okay, now when I plug in infinity, you can see that e to the x gets as large as it wants, and then you're just dividing that by 2. Well, that's still like infinity divided by 2. That's still infinity, right? You're looking at 1/2 of the limit as x goes to infinity of e to the x. Well, that's half of infinity. That's still infinity. All right, so when you're looking at this limit, it can get absolutely as large as it wants to get. But this is a situation where we use L'Hopital's rule once, right? This was giving us infinity over infinity, but we still got infinity over infinity. So then we applied L'Hopital's rule again, and aha, see how the denominator lost that variable x? So we were able to settle down on a nice limit. Well, settle down on a nice limit. It blew up. And you're thinking, well, why didn't you just give us this rule way back in day 1 in chapter 2? Because you're not supposed to abuse it, right? Things can go wrong if you just assume you can use L'Hopital's rule on every single limit. So let's take a look at finding the limit as x goes to, infinity of the natural log of x divided by the square root of x. Now, both of these are very slow growing functions. The natural log function grows forever and ever and ever, but it grows very slowly the further out you get. Same thing with the square root function. It does grow as large as you want it to be. It gets as large as you want, but it takes a very long time to get there. The question is, when we look at the ratio, do they grow at the same rate? Does the numerator grow faster, making this limit blow up? Does the denominator grow faster, making this whole thing, collapse down to 0 if we look at the limit out to infinity? So this is kind of one of those limits where you look at it and you say, well, if I plug in infinity, log of infinity is infinity, square root of infinity is still some sort of infinity, so I'm back in an indeterminate form. So we'll take L'Hopital's rule. Now I'm going to rewrite this denominator as x to the 1/2, just so you can see the differentiation a little bit easier. Again, we're going out x to infinity. Differentiate the top, you get 1 over x. Differentiate the bottom, you get 1/2 x to the negative 1/2. Again, no quotient rule happening here. All I'm doing is simply differentiating the top and then differentiating the bottom. I'm doing them separately, completely separately. So let's clean this up because this expression looks kind of gross. All right, so I've got 1 over x in my numerator. This is 1 over 2 times the square root of x. And so this is what we're looking at, some sort of like complicated expression here. Let's multiply by the reciprocal. So I'm not doing any L'Hopital's rule stuff or anything. I'm just simply rewriting this back in its square root notation, putting it where it needs to be in its denominator. And I'm going to multiply by the reciprocal. So that I can look at this and say, well, I have 2 square roots of x in the numerator. So the limit as x goes to infinity of 2 square roots of x over a whole factor of x in the denominator. That's x to the 1/2. That's x to the first power. So I'm just going to be left with square root of x in the denominator. Right, that's an infinity. Meaning that denominator is going to get as large as it wants, and the numerator is stuck. So this is just going to go to 0. The denominator keeps growing, and the numerator stays the same. So I'm getting a smaller and smaller number as I get larger and larger in terms of x. So that limit must be 0. So again, identify the indeterminate form, and you're free to use L'Hopital's rule. This one is find the limit as x goes to pi from the left, the one-sided limit, sine of x over 1 minus cosine x. Now, what happens if you just say, all right, I'm just going to use L'Hopital's rule. Who cares? I'm just going to use L'Hopital's rule, right? Wrong. This is not going to give you an indeterminate form. You cannot use L'Hopital's rule. In fact, if we try the limit as x goes to pi from the left of sine of x over 1 minus cosine x, we get the limit as x goes to pi from the left of the derivative of sine is cosine. The derivative of 1 is 0, so it's gone, minus the derivative of cosine, which is negative sine. So I get a negative sign in the bottom, that's just sine x. So when I look at this, as x goes to pi, cosine of pi is going to be -1. Sine of pi is 0. You may run the risk of saying that this limit would be negative infinity, or does not exist, or some other random cooked up number that you may find. Again, you were not allowed to use L'Hopital's rule from the get-go, because when you look at this, when I look at sine of pi over 1 minus cosine of pi, yes, sine of pi is 0. 1 minus cosine of pi is negative 1. This is 0 over 1 plus 1. 0 over 2 is 0. This is my correct limit. This is wrong. You were never allowed to use L'Hopital's rule. So do be careful. You have to really meet these indeterminate forms to have that ratio 0 over 0 or infinity over infinity or positive infinity over negative infinity or negative infinity over negative infinity, right? As long as you've got top and bottom are infinity, the plus and minus aren't important. Then you can use L'Hopital's rule. Notice it's a then, right? You have to meet that criteria first. Otherwise, you should not be touching L'Hopital's rule. Otherwise, you run the risk of doing something like this and getting a bad limit. So what about some of these other forms? They don't really look like a ratio top and bottom like f over g like these do. So when you come across limits where you might get this at first, what are you going to do with a limit when you encounter something like that? Well, here's just a couple of examples. Let's say we want to find the limit as x goes to 0 from the right of x times the natural log of x. So as x goes to 0 from the right-hand side, from the left-hand side it's undefined because we're dealing with the log function here. So that's why they're doing the one-sided limit from the right. But I plug in 0. If I plug 0 in for the natural log function, remember what the natural log function looks like as you approach 0 from the right-hand side. You're actually going down to negative infinity. So you're getting some sort of 0 times negative infinity, which fits one of these type of situations. Right? Does the 0 negate this infinite value, or is infinity much more powerful than 0? Well, we don't know. Right? And that's why they call it indeterminate. You cannot determine what that actually means as far as the limit is concerned. So what you need to do is play around with it so that you can get it into one of these two forms and apply L'Hopital's rule. So what you can do is take the limit as x goes to 0 from the right, and instead of taking the natural log function and multiplying by x, I'm going to divide by the reciprocal 1 over x. Dividing by 1 over x is the same thing as multiplying by the reciprocal of 1 over x. So this is x times natural log of x, if I were to reciprocate this. But now when you look at it in this form, as I approach 0 from the right, this still goes to negative infinity, the log function. And 0 here, 1 over 0, right? That's like going to infinity from the right as you approach 0 from the right. So now you're stuck in a form that looks like this, which means now you can apply L'Hopital's rule. Now you have the ratio of two functions f and g, and when you look at the ratio of those two functions f over g, you can apply L'Hopital's rule and instead look at the ratio of f prime, there's my numerator differentiated, over g prime, here's my denominator differentiated. All right, so again, this is really x to the negative first power. So I'll get a negative x to the negative 2 power, which is negative 1 over x squared. So now what we can do is look at the limit as x goes to 0 from the right. Notice the log function disappears once I differentiate it. So I get 1 over x. And I'm going to multiply by the reciprocal of negative 1 over x squared, which is negative x squared over 1. Which cleans things up nicely because now I have the limit as x goes to 0 from the right of just a negative x. Well, simplifying those powers and still having the negative is not contributing anything because x is going to 0 negative 0 is just silly. That's just 0. So I forced it into a form where I could apply L'Hopital's rule, and then apply L'Hopital's rule, and just a simple little algebra step gets us to where we need to go. So that tells us that our original limit here must be 0. And I'm going to leave that on the board for a second. And look at the limit as x goes to 0 from the right of x to the x. So now, when you look at something like this, you're in a form where if you try and plug in 0, you would get 0 to the 0 power, which counts as another indeterminate form. All right, that expression 0 to the 0 is really undefined. So how can we play with it? There's no way that I could make this like a numerator and a denominator without overcomplicating things, and it's still not going to get me anywhere because I'll still be staring at something like this x to the x. Well, what I can do is call this limit y. And instead of looking at this limit y, I'll look at the log of the limit. I will look at the natural log of the limit as x goes to 0 from the right of x to the x. Now, since we are approaching 0 from the right, and when we look at the log function and x to the x function coming in from the right-hand side as x gets closer to 0, we do have continuity, so we can swap the limit and the log using those nice properties that we have for limits. And we can say that the natural log of y is equal to the limit as x goes to 0 from the right of the natural log of x to the x. All right, so the log of the limit is the limit of the log. Thanks to that nice continuity that we have and those nice limit properties that we saw way back when. But now I'm doing log of x to the x power, which means I can use properties of logs to say that this is the limit as x goes to 0 from the right of x log x. Now you can't take the x outside of the limit, right? That's the whole point of the limit, is to let x go to 0. If you take it outside the limit, then you're not letting x go to 0. So it does have to stay within the limit, but look what we just found. We just found the limit as x goes to 0 from the right of x log x. We just found the limit as x goes to 0 from the right of x log x. We just found that in the last problem. So that tells you that the natural log of y is equal to 0. Right? We just found out that that limit must be 0. But we didn't want the natural log of y. We wanted y. We wanted this limit. So how do we get y back? How do we get our desirable limit back? We exponentiate both sides of this equation. E to the log of y is an identity for y. Right? When you exponentiate a log, right, that's the exponential function and the log function are inverses of each other, so you just get that y back. E to the 0 is 1. So that tells us that our limit as x goes to 0 from the right of x to the x must be 1. Right, because that's what we called y. So there it is, there's y. So again, some funny situations can happen. You know, this is one of those tricks where you're like, I would have never known to do that. That wouldn't have been my first guess. Yeah, it's one of those tricks where once you see it, you go, oh, I get it. And typically when you have things like, you're raising things to a power, and you've got like infinity to the 0, or 0 raised to the 0, or 1 to infinity. When you see one of these 3 things pop up right off the bat, which we had here, 0 to the 0, then this is usually the trick that you want to go for. Doing this log stuff and getting the stuff out of the power and boiling it back down to a previous limit. Now from here, having not done this problem that right beforehand, we would still have to continue finding this limit, because this would be 0 times negative infinity. So all the work we did for this problem would just be inserted here, but eventually we'd get to here and we'd get back to our original limit. But having done the previous problem, we can just do what I did here and refer back to it to save some space on the whiteboard. And then for forms like this, for these 2 types of forms, very typically you want to just make a little rearrangement. Right? I rearranged what I had when I had something like 0 times negative infinity or 0 times infinity. I had to rearrange it. Instead of multiplying by x, I divided by 1 over x. Right? That was just that's something that you have to do trial and error. Figure out which one you want to leave in the numerator and which one you want to reciprocate and put in the denominator. Because you could try it the other way, leaving the x in the numerator and then reciprocating 1 over log x. And you realize pretty quickly you get a really complicated expression that you don't want to mess with. So then go back and try it the other way, like I tried it. Leave the log x, but divide by 1 over x. And then I'll pick on one more, because we didn't do one with the infinity minus infinity. So let's say we want to find the limit as x goes to 1 from the right of 1 over natural log of x minus 1 over x minus 1. So let's start with, first of all, seeing what happens if we plug in 1 coming in from the right. Log of 1 is 0 in the denominator, meaning this piece would be 1 over 0 minus, again, if we plug in 1 in the denominator, it would be 0, 1 over 0. So we're getting this infinity minus infinity, right? We're getting these undefined or indeterminate type of limits here. We don't want that. But now, when we have infinity minus infinity, one thing we can do right off the bat, coming in, x goes to 1 from the right, of 1 over natural log x minus 1 over x minus 1. And if you try and break it up like, oh, well, I'll do this limit minus this limit, well, you're still going to get infinity minus infinity, and that's not 0. Right? We can't say that that's 0. Infinity is not a number. It's not a real number that obeys the laws of operations on real numbers. Subtraction is an operation that we use on real numbers. These are not real numbers. These are just concepts. Right? So now what we can do is take the limit as x goes to 1 from the right. I'll get a common denominator here, which means I'm going to have to multiply by x minus 1 top and bottom in the first expression, minus, I'm going to have to multiply by the natural log of x top and bottom in the second expression. So now I have a nice common denominator. This is the limit as x goes to 1 from the right of x minus 1 minus log x over my common denominator, natural log of x. I'll distribute that so it's x natural log of x minus natural log of x. So at least I do have one expression here rather than 2 being subtracted. And don't you dare cancel those log x's out. Division and subtraction do not play well together. We know that. So now what we have to do is see where we're at. If I plug in 1, what do I get? 1 minus 1 is 0, minus, well, log of 1 is 0, so the top's 0. 1 times, well, log of 1 is 0, so that's 0 minus log of 1 is 0, 0 minus 0 is 0. Aha, so I'm in an indeterminate form now where I can apply L'Hopital's rule. So let's go do that. Let's apply L'Hopital's rule. The limit as x goes to 1 from the right. And again, you never change this, right? You always take x and bring it to the same spot, right? That doesn't change. The only thing L'Hopital lets you do is differentiate the top. Derivative of x is 1. Derivative of minus 1 is gone. Minus derivative of log x is 1 over x. Now we want to differentiate the bottom. Be careful, there's a product of two functions here. There's the x times the natural log of x. So we do want to differentiate the bottom properly. I want the derivative of the first, which is 1, times the second, plus the first function times the derivative of the second natural log function. But there's still a minus. I need to differentiate the natural log, which is 1 over x. So I differentiated the bottom. I needed a little bit of product rule at first, minus, and then I differentiate that next term. Okay, still looks sloppy. So let's see what we can clean up. Those can be canceled out pretty nicely. I can say that this is the limit as x goes to 1 from the right of 1 minus 1 over x over natural log of x plus, this isn't 0 though, this is plus 1 over 1, or sorry, minus 1 over x. Well, too many 1 over x's floating around. Let's see if we can clean this up a little bit further by having everything get a common denominator here. I'll multiply by x, top and bottom there, so I get a common denominator x. I'll multiply by x, top and bottom here. I'll multiply by x, top and bottom here. So I really have x minus 1 over x in the numerator. I have x log x plus x minus 1 over x in the denominator. Now we'll multiply by the reciprocal. Right? I don't like this complicated expression, so I'm going to multiply by the reciprocal and have the limit as x goes to 1 from the right of x minus 1 over x multiplied by x over x log x plus x minus 1. Cancel these out. So now I'm looking at the limit as x goes to 1 from the right of x minus 1 over x log x plus x minus 1. Again, if we plug 1 in, the top is going to be 0, 1 minus 1. Log of 1 is 0, 1 minus 1 is also 0, so 0 plus 0 is still 0. We're still in an indeterminate form, which means we can reuse L'Hopital's rule. It doesn't mean we're stuck. It doesn't mean we're at a dead end. Right? If we got the exact same expression back, which we didn't, right? It's not exactly the same, but if we got the exact same expression back, then we would say, okay, now at this point we're just going in circles, which can actually happen, right? But we have something different. So, well, I'll leave the original limit there. And again, excuse me, I don't have the largest of whiteboard. But that's the original limit. We're good up to this point. Don't worry, we're almost done. All we got to do is try L'Hopital's rule again. Differentiate the top, we just get 1, right? Because it's simply just a linear function, x minus 1. Differentiate the bottom. Again, there's a product rule that we have to be aware of here, right? So it's the derivative of the first times the second plus the first times the derivative of the second. Then I differentiate this x term, that's just 1. Differentiating minus 1, well, it's gone. So again, let's just clean it up and say the limit as x goes to 1 from the right, 1. Right, that is very helpful because now I know I can't use L'Hopital's rule. I'll never have 0 over 0 or infinity over infinity because I'm stuck with 1 in my numerator. When I look at this and clean it all up, same thing happens like happened before. X over x, we can simplify that. That's 1 plus 1, so that's 2. So it's ln of x plus 2. Now let's let x go to 1. Aha, natural log of 1. This thing is going to approach 0 because log of 1 is 0. So I'm looking at 1 over 2 for my limit, a half. All right, and the reason I left that original problem up there was there's no way you could have gotten 1/2 from infinity minus infinity, right? That's why we call these indeterminate forms. You cannot determine that this limit is 1/2 just based on looking at that. Because the next time you encounter infinity minus infinity, the limit might be actually 7. The next time you encounter infinity minus infinity, the limit might actually be -5. There's no way to determine it based on the information here. You've really got to fight with it. And by fight with it, I mean, L'Hopital's rule, take some derivatives, do a little bit of algebraic manipulation, and then you're pretty much home free. So there are 1 through 65. Of course, odd. Yeah, I think odd is more than enough there. I just didn't write it. So practice some of those limits. They'll be useful for the next section when we look at graphing more complicated functions. Again, we want to use the first derivative for max and min, increase, decrease, second derivative, inflection points, concavity up, concavity down. We're going to bring some of these limit concepts into the picture to see where the limit goes as x goes to infinity, where the limit goes as x goes to negative infinity. We're going to look at the vertical asymptotes as well. So a whole bunch of stuff. It's all going to come together in one big picture in the next section, 4.5. And then I believe we skip 4.6 and then jump to 4.7 after that. 4.7 is more like the word problems, basically optimization. So yeah, I will see you for 4.5, where we'll be doing just a whole lot of graphing.